Einstein in 1906, An Alternative History. This is a talk I gave at the fall APS meeting in 2015 at Dartmouth University. And we see right in the middle there Einstein and his math buddy Marcel Grossmann. Einstein was not so good at math. He, in fact, skipped the graduate level math classes he was supposed to take, but Grossmann took really excellent notes and really understood high math. And Einstein eventually realized that there was a deep problem with special relativity, particularly with regards to dealing with gravity. And that's when, in around, I think it was 1912, he turned to his friend Grossmann again and said, I need some help with the math. The math he needed help with was known as differential geometry. And that's represented in cartoon form on the right. It's a lot of stuff that was hard to figure out then, and is it still pretty hard to figure out today. You need things like tangent spaces and cotangent spaces and the Riemann curvature tensor and manifolds, and you finally end up with a metric that can characterize curved spacetime instead of flat spacetime. And after 3 years of some of his most intense work of his life, he ended up with general relativity to explain how gravity works. And that has been an awesome theory. It makes tons of predictions. Every one of them has been confirmed. We have the utmost respect for that body of work. But it still ain't easy. Now, the Perimeter Institute is a relatively new Center for Theoretical Physics, and they had a meeting called Convergence, where the kind of message I got from the organizers was, we really hope to get math that was like as easy as it was in 1905. It doesn't get so impossibly complicated. They didn't find it, but that's kind of what the hope was. And in a certain way, that's what this talk is about, because I think the math here is going to be manifestly easier than differential geometry, but I'll let you make the judgment on that call. So let's really review those 1905 results, and in particular we're going to show that there actually are links between them. Okay, so 1905 is just a miracle year for Einstein. He came up with all these ideas like special relativity, the physics of going fast. And he came up with this mass-energy relationship. Photons have a new kind of form, and then there is Brownian motion. But let's actually get to the math, because that's what matters to me. So there's this thing called the interval squared, which is time squared minus space squared, and we're going to see that over and over again in this talk. So then mass energy, E equals mc squared. There's also this momentum thing, but it's a squared difference. Now, the photon hypothesis also has a momentum hypothesis going along with it. And then Brownian motion was a bit of statistical analysis where he said, it's the variation. Anyway, so what happens if you divide through by dt? Well, you get 1. Sorry, the interval, d tau. And so you have all those, the difference of these two differentials. Well, let's repeat that process, because we'll again get 1, which is kind of cool. But there really is a relationship between this dt d tau and energy, and dr d tau and momentum. But we can also substitute our quantum relationships, those ones with h in them, into the expression, because that's a perfectly legal thing to do in terms of algebra. And so now you can see that these three of these four relations things that he got in his miracle year are actually related to each other by this what's in that green box. Now, what was he really doing in that green box? He was doing a lot of squares. Well, that's kind of like got a really old tradition to it, squaring things and saying, hey, there's a relationship between the squares of these things. As a matter of fact, it goes back to the Egyptians. that's quite a while ago. And then, of course, there was Einstein. And I'm going to bring in Hamilton, actually. Not the American, but the Irish physicist. So we've got this distances squared sort of thing. And Einstein said, oh, well, if you're moving, we should need to take into account changes in time to get the interval. And Hamilton actually had this thing called a quaternion, and it's also got some squares. Oh, and it's also got to do 2 dt dr, okay? Because that's a perfectly fine thing to do with dt and dr. So Egyptians were the BC. Einstein was 1905, but Hamilton came up with his idea in the 1840s. So why aren't we talking about Hamiltonian's relativity? And the reason is this, like, foreness of it surprised him so much that the first thing that he did was he defined a pure quaternion where the dt is like equal to nothing, 0. So he kind of said, yuck. He didn't embrace it, which is too bad, because the history of physics would have been very different if he just said, that's the math, I got to deal with it. All right, so let's think about intervals in space-time. So this is like the distance between two events. I like to think of it as specifically finger snaps. And what do we say about the distance between finger snaps? Okay, so there's going to be this special sort of interval, and then there's going to be the general sort of interval. Our math here is that interval, d time squared minus space squared equals d tau squared. Now, if we want to generalize it, what this means is we don't put constants in front of the dt and the dr, but we come up with some kind of function, and that becomes a very kind of, that behaves differently. And we call this working in flat space-time. And this is curved space-time because it's no longer, well, flat. It's different from being flat. But the big question to me is, where is dt dr? Because it's totally legal to do something like that. Now, there are whole areas of studies in physics where they say, oh, we're losing information. This is a case where we're ignoring information. It's totally valid to form that sort of mathematical object. It never gets formed. It never gets looked at. So it's kind of like the physicists are guilty of ignoring information that's there, and obviously there if you happen to use quaternions. So let's use quaternions to try and figure out special relativity, the kind of the physics of going fast, and see what we can see out of that kind of situation. So who are we going to deal with? Well, we are going to always deal with the reference. And the reference is always easy. It's always what you expect. And then we've got this person who's speedy, but actually running away. So the reference is going to be just take dt dr, square it up, and you end up with that interval thing, and dt dr, which I call space times time, by the way, because it's space times time. Okay, so if you're running away, it means that your time is actually greater because you run away. And the distance actually looks greater too because you're running away. Now, it doesn't increase by exactly the same amount, those two values. They're a little bit different. But what's really important is that one interval exactly equals the other interval, even though that, the times going in are different. So the speedy away values, both dt and dr are larger, and therefore its space times time is larger than the reference observer. But of course, since physics, standard physics, just completely ignores it, I mean, that's no big deal to them. But I think it's important to not ignore information like ever. Okay, so we're going to see whether we can deal with gravity or not, because that would be quite radical, just doing it with algebra. All right. So who's involved in this process? Well, I bet you know one person, the reference. Okay, and then we introduce you to Balloon Man. Okay, so he's in a balloon. He's not under as much stress from gravity as the reference who's sitting closer to the Earth. Okay, so the math here, you bet it. It's going to be just take that interval, just that the measurement, square it, and you end up with the typical kind of thing that you see. This time, we say, well, what's the time? The time, his heart can beat faster because he's not under the stress of gravity. And his ruler is larger. And if you have a large ruler, like I do, then everything else looks smaller, okay? So dr actually gets smaller. So the interval, it's got a bigger value minus a smaller value. Bigger minus smaller makes it just bigger. Okay, that's cool. And this one is smaller. Cool. But here's where our hypothesis is that those guys are equal. Okay, so this is really my proposal. That thing you were ignoring before, shouldn't have done that. Because all you got to do is say those guys are equal, and maybe you've got a brand new handle on a way to deal with gravity. Okay, so we can actually express this kind of mathematically. I had to go to a place called Math Stack Exchange to find the fancy name for this. I kind of like it now. It's called equivalence classes for special relativity and my quaternion gravity proposal. So we'll get our definition. It is a subset created by an equivalence relation. Ooh, doesn't that sound official? Okay, so what do we mean? Well, we start with quaternions, both of which are an element of the set of quaternions, but we're actually looking at differences of quaternions to kind of eliminate the origin. And then we actually had to come up with this thing I call a distance function, because people are going to want to pick different sorts of coordinates, and the distance function will kind of manage going from, say, spherical to Cartesian and all that kind of stuff. But this distance function acting on the difference between two quaternions is still a quaternion. Okay, so what is special relativity? So we've got this distance function is equivalent to the primed distance function if the real part of the distance of the unprimed guy squared equals the real part of the primed guy squared. All right? And then quaternion gravity is like its counterpart. We're saying those two are equivalent, the unprimed to prime, if the imaginary part of the distance function of a delta squared is equal to the imaginary part of the distance of the delta prime squared. Okay? And that's kind of basically it. Those are the two proposals. You can see they're like next door neighbors. One's real, about the real numbers, and the other's about the imaginary numbers. And I like to say this is just kind of like an upgrade on Einstein, who was just an upgrade on the Egyptians. Einstein brought in, time, and then I'm bringing in space times time. And that's like all it is. Okay, but we had to get precise about this proposal because there are precise measurements of weak gravity fields, and we got to match them, because if we don't, this is an immature proposal. So what properties must it have? Well, it's got to be flat, as this ratio of mass to distance goes to 0. And the space times time part, that the dr thing, that part has to always be constant. Doesn't matter where I am in space, it's got to be the same. So then there are the experimental tests, so it's got to match those of today, and anything in the future, well, actually, maybe if we do it higher resolution, it should be different. So we think about what's going on locally in that curved space-time, and if you're just right there, I mean, you don't see anything, so you just, you know, it's the usual thing. It's like the reference. But if you get far away and you're comparing the local to the far away guy, that's when I'm proposing you get this exponential function. It's like, but why an exponential function? Well, because exponential functions show up everywhere in physics. I mean, that's the calling card of an advanced theory. And so we're going to square this sort of thing. All right, and so we get, a 2, minus 2 dt, and we get another 2, but it's got the opposite sign. That's the way things in gravity fields work. One goes up, the other goes down. And we have our space times time, which when you do an exponential with a plus to the minus, cancels out. Okay, so if you put 0 in there, you get 1, so we get flat space-time. And that's always constant because we got the perfect cancellation. And then we've got this thing, which is actually known officially as the Rosen metric. And it's to first order ppn accuracy, it predicts the same thing. But to second order, it actually says there's going to be 6% more bending of light, which is kind of cool. It means, you know, if you don't like this proposal, who cares? Let's just give it to the experimentalists. Let them decide it the old-fashioned way by doing the experiment, which, by the way, is really beyond our reach at the moment. When they did the light bending around the sun experiment, that was all well and good. There was a factor of 2 different, but to do this at second order ppn accuracy, you had to go out literally 6 significant figures to get this little effect, and deciding that little effect is not due to, say, a quadrupole moment of the sun or the way stuff spins inside the sun. Oh my goodness, that's really, really hard to do. So it's not like, yeah, we're planning on doing this next year, testing this second order ppn. It's really hard. Okay, so now we're coming to something that this proposal can do that general relativity cannot, and that is have electromagnetism tell us directly about geometry. All right, so there's this thing called a Poynting vector, which we will define momentarily. And so we've got a little bit of math about EM, and that is we're going to take 2 types of combinations of fields, the difference of E and B, and minus the sum of those 2 guys. We're going to multiply them together just because we can. They're quaternions, and we get this b squared minus e squared, and that E cross B is the Poynting vector. Now there's this thing called the Lagrangian, and it's used to do all kinds of calculations. But this Lagrangian here happens to be Lorentz invariant. It takes a bit of work to get that proof, so we'll skip that sort of thing. If you do the calculation of variations on that Lagrangian, you actually get Gauss's law and Ampere's law. And I think I have a video or 2 on how to do that explicitly. But we're skipping those details, because what matters for the Quaternion gravity proposal is that this E cross B thing should be the same if you are in the valley or if you're at the mountaintop. And the reason is that the proposal is purely algebraic, and it says if you have if your kind of first term in your quaternion is Lorentz invariant, then that term that's next door to it is going to be the same if all you've done is moved in a gravitational field, gone up or down and that sort of thing. And if you go up and down, it's got to be the same. Okay, so that is a separate test of the proposal, and oh, I'd love to be able to do that. Okay, so now we're going to finish with a kind of long calculation. It's the equations of motion, and it's kind of like the third example of where we're using this this little bit of algebra, but we're starting with a different equation. The equation we're starting with is energy momentum in curved spacetime. Okay. And we're going to try and make it a little bit easier. We'll work in the equatorial plane. That'll eliminate one of these terms. In fact, that one right there. Okay, and now we got the curved spacetime, so we have our exponential thing. And see, we're no longer in an interval. We're dealing with energy and momentum. And another technical point is that we're in what's known as Schwarzschild coordinates, which means all the change is happening in the dr d tau, not in the d theta d tau. So we're going to square this thing, and we're actually going to only look at the first term. Okay, so you square energy momentum, you end up with mass squared, and then we've got our two exponential guys and our angular guy. All right. There's Mr. Angular. Now we're going to focus on the dr d tau term, and let's just bring that over, and let's forget our r squared. Oh no, I put it in afterwards. Okay, so that has the right units. Okay, and now we notice that our energy momentum thing that we started out with didn't have a t or a phi. So that means energy and angular momentum are conserved. There's no kind of like a damper on it to make it change over time. So we kind of look back up to that first line, and we kind of do some substitutions. So there's angular momentum now, and we got energy here. And it's all well and good. And then we're just going to keep first order terms in this gm over c squared r, and we end up with this expression, which if you know or don't look up on the internet, you'll see is basically the equations of motion that appear for the Schwarzschild metric of general relativity. And so to first order in that term, we predict the same things for like the precession of the perihelion of Mercury, which depends, of course, on the equations of motion, and since they're exactly the same, the results are going to be the same. That goes for just all the weak field tests. All right, so in summary, I think this body of work has the 1905 spirit because it's algebra, and it's only algebra. We did not solve a field equation. So Quaternion gravity is going to head against general relativity. One of these proposals is right, the other is wrong. And this is in the classic sense of right and wrong. General relativity will always be a most elegant and excellent and consistent with all kinds of test kinds of proposal. Quaternion gravity is trying to accomplish all the same things, which by that last calculation you say, well, it certainly can to that order. But if we crank it up a notch, maybe things are going to be in favor of Quaternion gravity, or maybe general relativity wins again. Okay? But the point is, let's let second order PPN tests decide the issue. I think the biggest conceptual advantage of the approach is that EM can be defined geometrically. See, when you do the Maxwell equations, you can do it in flat spacetime. You can do it in curved spacetime. But somebody else, I shouldn't say somebody else, some other equation has to decide what your metric is. That's not the case here for quaternion gravity. For quaternion gravity, the EM fields can tell you, oh, this is what's going on geometrically. And that's pretty powerful. All right, so there are no fields. It's an algebra thing. There's no fields for special relativity. It's just, you know, that everyone has to obey special relativity. And my proposal is everybody has to obey the rules of quaternion gravity, which is about the space times time. So there's going to be no field, no graviton. This whole issue of quantizing gravity, oh, you don't have to do it. You can skip that. There is without a graviton, there's nothing to quantize, and so that would be rather radical. And actually, even more radical is that it suggests that we should always use quaternions and not use tensors. And that's going to be next to impossible to sell. But in the spirit of 1905, I still feel pretty good about this proposal, this new proposal for dealing with gravity known as quaternion gravity. Thank you very much.